Again, some things to sort of keep in mind anytime you're doing any of these problems in which you're asked to describe a galvanic cell. I'm going to put an ox, I'm going to put red cat, and I'm going to put fat cat. As we look at these two half reactions that are provided to us as we try to build this galvanic cell, we've got a positive standard cell voltage for both of them. The one that's most positive is going to indicate for us our reduction half reaction, which is the second one here. And again, you're going to determine that simply based on which one is higher. This one's got a higher reduction potential. And so as we describe this cell, we're going to rewrite CR207. This one's taking place in acidic conditions, indicated by those hydrogen ions there. Positive 1.33 volts for this reduction half reaction. The oxidation half reaction then is going to be the reverse of what we see here. So we're going to end up with solid copper losing electrons to form the copper 2+ ion in solution. Now, before we move on, we need to make sure that we, one, flip the sign of the oxidation half reaction, so it's going to be negative 0.34 volts. And then we want to make sure that we are gaining as many electrons as we are as we're losing. Currently, we've lost 2 electrons, so we've gained 6. And so to remedy that, we're going to multiply this oxidation half reaction by 3. And again, the reason why we do that is we want to make sure that we are gaining as many electrons as we are losing. Our electrons will now sort of drop out of this combined redox reaction. We're going to end up with CR207 2 minus plus 14 plus 3 Cu on our reactant side, and then we're going to get 2 Cr3 plus 7 waters plus 3 Cu ions. So there's our balanced redox reaction, the standard cell potential for this galvanic cell. We're gonna add these two together to get positive 0.99 volts. As we take a look at describing this in a cell diagram, our anode, which is where oxidation takes place, we're gonna have solid copper anode in a copper 2 solution, connected by a salt bridge. Once again, this is an example where we have just a bunch of ions in our reduction half reaction. We've got the dichromate ion, in which our chromium is at an oxidation state of +6 and is reduced to an oxidation of +3. So we've got, again, 2 ions in solution here. We're going to include not only those ions, but also the hydrogen ions. So we've got Cr207 2 minus, the H plus, and the chromium 3 ions. Again, we need to have a solid electrode here for those electrons to flow. It's going to be a platinum electrode there. And then finally, let's sort of draw this out in a picture format. We've got our 2 half cells here, connected by a salt bridge. Boom, there's my salt bridge. In this half cell, we'll put our anode, which is the copper. And in this half cell, we'll put our platinum electrode, again inert, just so our electrons can flow through that to reduce the chromium in solution. Here's our 2 solutions. This is going to be a solution. This is going to be a copper solution over here, while over here we'll have our dichromate ion in acidic conditions. The last thing we want to describe is our flow of electrons here. As we think about the flow of electrons, again, it's always going to be from the anode to the cathode. And as I've described it here, I've put the anode on the left. So we're going to go in this direction. So our electrons are going to flow from the solid copper across the wire down the inert platinum electrode into solution, reducing the chromium in the dichromium ion to the Cr3+ state. It is a good idea to make sure you include some salt in your salt bridge here. Again, the go-to for me is potassium nitrate. That will work for you all the time. Okay, people, let's try this one more time. We're going to move pretty quickly through this last example of a galvanic cell. Again, you have to be able to take a look at a couple of reduction half reactions and build a galvanic cell based on just the information that you provided in those half reactions. As you do that, I would highly encourage you to go back and fall back on these mnemonic devices, Anox, RedCat, and FatCat. They will help you out immensely as you work through trying to build these galvanic cells. So first things first, as we take a look, remember you're going to be giving them as reduction half reactions. You have to examine the reduction potentials to determine which one is going to be your actual reduction half reaction, and then from there determine what the oxidation half reaction will be. As we take a look at these two, the one that's most positive in this case is the first one. So this will be our reduction half reaction. I'm just going to rewrite that. Again, the hydrogen ions indicate this is taking place in acidic conditions. And our reduction potential positive 1.00 volts. The second reaction then we're going to reverse so that it represents the oxidation half reaction. Remember then your reduction potential becomes the oxidation potential by simply reversing the sign. Then we need to combine our two reactions, but before we do that, we want to make sure that we are gaining as many electrons as we are losing. In this example, we are only gaining 1 electron but losing 2. So to balance our half reactions out, we need to multiply our reduction half reaction by a coefficient of 2. When we do that, our final combined redox reaction is going to look a little bit like this. Again, our electrons will cancel out now that we've balanced it. 2VO2 plus. Some zinc ion in there. And then our standard cell voltage for this galvanic cell, we determine simply by adding together the standard reduction potential for the reduction half reaction and the standard oxidation potential for the oxidation half reaction. And in this example, it will give us 1.76 volts. Nice positive value there, indicating some highly spontaneous, thermodynamically favored reaction is going to occur. If we were then to draw a cell diagram for representing this galvanic cell, we would have our anode described first, which is the oxidation half reaction, which means we're going to start with our zinc electrode in a solution of zinc ions, separated by our salt bridge there, followed by, once again, I've chosen an example in which we have just a bunch of ions in solution, so we will need an electrode that is inert for those electrons to flow through and then reduce our VO2 plus from the vanadium 5 ion, or from a vanadium with a positive 5 oxidation state to a vanadium with a positive 4 oxidation state. We're going to include those hydrogen ions in there. Let's see, VO2 plus. There we go. And again, we're going to choose platinum as our inert electrode there for the reduction half reaction. Whoa. Come back. All right, then lastly, let's draw a quick picture of our galvanic cell. We have our 2 beakers for our, or chambers for our two half cells here. In the one on the left, I'm going to put my, you know what? Let's do this one on the right this time. I'm going to put zinc over here. Again, it's totally up to you how you want to draw the picture. The cell diagram, however, has to be anode and then the cathode. And then over here, I'll put my platinum, PT. Connect us here with a wire. And then our solutions. Got our two solutions in here. We'll have our zinc ions in our solution over here. So as those zinc atoms on our zinc electrode lose electrons, we'll be pushing more and more zinc ion into solution. Over in our reduction half reaction half cell, we'll have all of those vanadium ions in solution. Always a good idea to include a salt in your salt bridge, and as in the previous examples, I'm going to use potassium nitrate. The electron flow here, I switched it up on you. I put the anode over here on the right-hand side. Again, just remember fat cat. It's going to be electron flow is going to go from the anode to the cathode. And in this example, it's going to be reducing the vanadium with an oxidation state of +5 in the VO2 plus ion to an oxidation state of +4 in the VO2